I am. All right. Well, good morning, everybody, or afternoon, whenever you happen to be watching. I think we've got about 4 of you online live here. Welcome to chemistry. I've missed being your chemistry teacher, but I'm sorry I'm not Mr. Ridgely. I know that all of you are probably missing him this morning. Kind of gotten used to him. He is a better teacher than I am, much more thorough. But he doesn't have the distractions that I have. I don't know, something about that Abeka class, man. There's just no tomfoolery going on in there. But anyway, all right, so we're going to go over, I just want to make sure we had a good opportunity to review a couple things for your test. And I went ahead and made up a test for these 2 chapters that was a little bit more reasonable and didn't quite have the intensity that the Abeka test had. However, you are still going to need to study, and you're going to want to pay close attention to your chapter reviews, chapter 12 and chapter 13 reviews, which we're going to go over here today in class. Go back and look at your exercises, you know, the concept reviews and all that kind of stuff, and then take a look at your quizzes that you have back. I think there may be one that you don't have back for chapter 12 and 13, but that's not going to affect you too terribly. We'll make sure that you have the information you need. But those are the things that you need to study. Study your bold term definitions, and make sure that you understand those concepts, and you'll do well on this test as long as you've been paying attention to the videos and taking note. I want to make sure that you're able to do the math that's going to be required, and you know the steps in that and the types of problems that you're going to have to do. So make sure that you've got some notebook paper ready, your calculators ready, so that you can do some of these problems with me, and just go ahead and copy those steps down so that you'll be able to do those steps when it comes time for the test, all right? So we're going to start on chapter 12. If you can kind of find your chapter 12 reviews that you did, pull those out. Make sure you have answers similar to this. So I'm going to go through this pretty quickly just to make sure you have correct answers. So double check and make sure your answers are correct. Mr. Ridgely has gone over these with you. Chapter 13 you have not gone through, but I do want to talk about these just in case something pops up that I want to draw your attention to for the test, all right? In a given solution, the substance that is the solute is what? The substance that is being dissolved, okay? The solute is the substance being dissolved. The solvent is the substance that is doing the dissolving. So definitely know those two terms. That'll come up a couple times. We'll skip number 2 for right now. It's not pertinent to what we're doing. Number 3. What is meant when two substances are described as miscible? That's how you say that, miscible. And to me, that sounds like mixable, okay? So that's how I remember that. But that means if two substances are miscible, they are completely soluble in each other in all proportions, okay? So all the gases that are in our air that we breathe are miscible. They're completely soluble in all proportions. You're going to get an even mixture of that throughout the solution of air that we breathe. And that can be true of a gas, and then it would be true within a liquid. So alcohol, ethyl alcohol, and water are completely miscible. They're going to completely mix, and you're going to have equal parts all the way through that mixture. That means they are miscible. Number 4, distinguish between solvation and dissociation. All right, so solvation is the process in which solute molecules or ions are surrounded by solvent molecules. Okay, so again, the solute molecules, those things being dissolved, are surrounded by solvent molecules. All right, so that happens when things are in solution. Dissociation is the separation of ions from each other that occurs when an ionic compound is solvated. So an example of that would be salt water. Okay, we have NaCl, and it dissociates into its respective ions, which would be sodium and chlorine, right? The sodium being the positive ion, the chlorine being the negative ion. And those ions are going to be completely surrounded by the water, the solvent molecules, the water molecules. Okay, so that's solvation and dissociation. All right, when you drop a sugar cube into a cup of tea, the cube begins to dissolve slowly, right? And that has to do with surface area on the sugar cube. You only have so much surface area of that sugar that is surrounded by the water and can come into contact with those water molecules. So how might we get the sugar to dissolve more quickly? And this is one that's come up over and over and over again. The first one is stirring. Okay, so certainly we can stir. All of us are familiar with sweet tea in Texas. There was a day when you had to make it yourself at the table, right? And you had to pour the sugar in there, drop the sugar cube in there if that's all they had, and you could stir it. You could crush the sugar cube, right? So in stirring it, you're actually getting the molecules of the water to come in quicker contact with the sugar molecules, and they're breaking apart and breaking apart and breaking apart, so that motion does that. Also adds a slight amount of heat, but not tremendously. And then you could crush or grind it, exposing more surface area of the sugar to the water, or you can increase the temperature. So you know that if you have a cup of hot tea or a cup of cold tea, which one is going to mix the sugar faster? It'll be the cup of hot tea that'll do that, because again, the heat adds kinetic energy to the mixture, and that allows the molecules to move faster. All right, number 6. What is meant by the principle like dissolves like? And that's a good general principle, and there's a concept question that comes out of this, okay? So the more alike two molecules are in terms of their bonding and intermolecular forces, in other words, how those molecules are put together, the more likely they are to form a solution. So the example that was given in one of your quizzes is if you have a polar solvent like water. Okay, so water is polar. If you remember our diagrams on the board, we have H and then we have two O's, right? Okay, and remember that is polar, all right? It has a positive and negative side. And so that is what it's like. It is more likely to form a solution with another polar molecule, okay? So if you had the choice between a non-polar molecule and a polar molecule, which one is more likely to dissolve in the water? Well, the polar molecule, because it's like water, okay? Like dissolves like, all right? Number 7, in your own words, explain what it means when a solution of sodium chloride in water is said to be saturated, all right? So we have saturated, unsaturated, and supersaturated. Saturated is at a given temperature, the solution has all of the sodium chloride, all the salt it can possibly contain under equilibrium conditions, all right? And those equilibrium conditions means that you are going to have some evaporation, but at the same time it's going to be going back into solution. So you've got all that you possibly can have in that solution at a given temperature. For something to be supersaturated, what we have to actually do is heat it up and then mix in as much as we possibly can with it heated up. And the way you can tell that, so let's just say you heat it up to like right at 100 degrees Celsius, your water, you mixed in salt, you mixed in salt, you mixed in salt until you can't mix any more salt. And you tell that because at some point you're just going to see salt on the bottom of your container, all right? When that cools down, that salt will remain in solution, but it's way more than it should have been able to hold had you just mixed it in at room temperature. So it is super saturated at that point, okay, because you mixed it while it was hot. Saturated is, hey, just at room temperature, I've got as much in there as I can, all right? As a rule, number 8, how is solubility affected by increased pressure? Okay, so is a molecule going to be more soluble if you increase the pressure? And so the first thing to know is that increased pressure has little effect on solid or liquid solutes. Okay, so if it's a solid or a liquid, pressure's not really going to do anything to it. But we know pressure affects what phase of matter, what state of matter? Gases, right? So that's the one that's going to be affected by increased pressure. And as you increase the pressure, the solubility of a gas increases. And you need to know that that is Henry's law, okay? And that just makes sense. If we're increasing pressure, we've got more molecules coming into contact with the liquid because of that increased pressure, and that, therefore you're going to have more solubility as a result of that increased pressure. Now the next question is about temperature. Increased temperature generally increases the solubility of solids and liquids. Okay, and we said that just a second ago, right? If I increase the temperature, I can put more salt or more sugar. It's easier to mix in, and I can actually get more in. So they're more soluble with a higher temperature. Same is true with liquids. So solids and liquids, as you increase the temperature, you increase the solubility. But with gases, if you increase the temperature, that decreases the solubility of the gases. Why? Because those gases are going to have more motion and they're going to be spreading out, and so you're going to have less gas molecules coming in contact with your liquid, and so they're going to become less soluble at that point, all right? Number 9, distinguish between molarity and molality and give the abbreviation for each. So this is definitely something you need to know for your test. So molarity, what is the abbreviation? Say it if you know it. Okay, it should be capital M, right? And then molality is a what? It's going to be a little m, right? And usually they kind of italicize it, okay? Both of these are measurements of concentration. Concentration is how much of a substance is mixed in with another substance. So if something is highly concentrated, right? In East Texas, we like highly concentrated sweet tea, right? We want it to taste like pancake syrup, right? I don't. I like a less concentrated tea, right? I don't want it quite as sweet. So So in science and chemistry, we've got these terms of molarity and molality, and we've got two different types because for different procedures, we need these two different measures of concentration. So the first one is molarity, and the formula for molarity is the moles of solute per liter of solution. Okay? Moles of solute per liter of solution, and that's the whole solution. That includes the solute and the solvent all together in per 1 liter of solution. Okay? Molality is moles of solute per kilogram of solvent. Make sure you note that distinction. So we're actually measuring at this point, or giving a ratio between how much solute do we have in moles, right? And that's actually a calculation of the number of particles, right? Avogadro's number, per kilogram of solvent. All right, and that's a mass measurement. This is a volume measurement, but this is a mass of your solvent. So at this point, it's not the whole solution, it's just how much solvent are you putting it into. Please make note that this is in liters and this is in kilograms, which means if you get a problem that gives you milliliters of solution, you're going to have to convert that to liters, okay? And that's pretty easy to do. If I have 500 milliliters, all I do is move that decimal place over. That's 0.5 liters. Okay, that's all you got to do. Very simple. Same thing with kilograms. If they give it to you in grams, you're going to have to convert that to kilograms. Okay, same kind of procedure. So make sure that you go through that procedure when you do those problems. And we're going to do one of those problems here in a little bit. All right, so molarity and molality. Okay, you need to know those two terms and how to do those math problems. We'll do that in a second. Number 10, what is the vapor pressure of a liquid? What effect does increased temperature have on vapor pressure? So vapor pressure is the pressure exerted by the vapor when a liquid phase and a vapor phase are in equilibrium. Okay, so you have a container of liquid, right? And up down here you have the liquid, and up here you have a gas, okay? And there is a pressure that is exerted by molecules, if this is water, by liquid molecules that are vaporizing up into the gas, okay? And that's called the vapor pressure, all right? So if I increase the temperature of this liquid, it kind of makes sense, right, that I'm going to be liberating more gaseous molecules of that liquid, and it's going to be applying more vapor pressure at that point. So if I increase my temperature, then I increase the vapor pressure. Number 11, what are electrolytes? Electrolytes are compounds that dissolve in water to produce ions that can conduct an electrical current. Compounds that dissolve in water to produce ions that can conduct an electrical current. You hear about electrolytes in athletics, in sports, right? You need to be hydrated, that's one thing, okay? Your cells need to be hydrated, but you also have to have electrolytes in there. So calcium, magnesium, sodium, those salts need to be inside of our bodies in order to conduct electrical current. Why is it important that our bodies can conduct electrical current? Because our heart, our circulatory system is an electrical current system. Our neurological system is an electrical current system, right? So the brain is sending electrical currents to the heart, to the body, and that's what keeps everything working. And so we need electrolytes in our blood and in our cells and so forth to make sure that we can conduct those electrical circuits. If you're not hydrated and have electrolytes, then your body starts shutting down. It's not able to perform as well. Number 12, in your own words, explain why osmosis occurs when distilled water and seawater are separated by a semi-permeable membrane. Toward which side of the membrane would the water molecules flow? Okay, and so there's a picture of this in your textbook. Where is my, oh, it's right here. I'm looking at it. That's funny. The semi-permeable membrane, you should be familiar with. Let me kind of find it on page. Hold on, sorry, I'm burning a little time here. Okay, so this is on page 214. All right, page 214, you can see osmosis taking place. And they have the pure solvent on the left side, and then a semi-permeable membrane, and then the solution on the right side. And the gist of this is that that semi-permeable membrane has, for lack of a better term, holes in it. Okay, it's semi-permeable, so that the smaller particles of the solvent, for instance water, can pass through, but the larger particles of the solute can't go the other way. Okay, they can't go back the other way. So which way is it going to flow? Well, it's going to flow from the more pure side, the solvent side, over into the mixture side. Okay, so osmosis can occur any time that there is a difference in concentrations of solutions on either side of a semi-permeable membrane. Seawater is more concentrated than distilled water. So if I have a container and semi-permeable membrane, and I have distilled water here and seawater here. Seawater is more concentrated because it has what in it? It's got salt in it, right? So it's a solution of salt. So it is more concentrated than distilled water. So the flow in osmosis naturally occurs from the more dilute solution. Distilled water has nothing in it. It's totally dilute. Okay, there's no solution whatsoever. So it flows from the more dilute, the pure water, to the more concentrated solution. So it's going to flow this way. Okay, it's going to flow that way. What's going to happen to the seawater as a result? The seawater is going to become less concentrated as that happens, right? So and we would have to kind of provide a source of distilled water and press in to that seawater. Okay, so number 13, let me see if we need, okay, distinguish between a solution and a colloid. You should be very familiar with that. You did a lab experiment on that, or you watched a lab experiment on that. 3 everyday examples of colloids. So a solution is a homogeneous mixture, right? It's all mixed together. Everything's the same in it. If you took a sample of any part of that solution, it's all going to be the same. It's homogeneous, in which the molecules of solvent and solute are thoroughly mixed. Why? Because they were, what's that word? Miscible, okay? A colloid is a heterogeneous mixture consisting of tiny clumps or particles that remain suspended within the mixture and is therefore not evenly mixed. So if I took a sample from different parts of this colloid, I'm going to get different amounts of the substance that's in there, and just kind of clumps that are in there. And there are examples of those colloids given in your book on page 218. You don't need to come up with any, but right off the bat, milk is a very common colloid. And I think honey also is a colloid as well. All right. Now those colloidal particles, this is number 14, remain suspended in the colloid, and they don't settle. Okay, they never settle down to the bottom. All right. Why don't they settle? There's a phenomenon. You need to know this. Okay, I can tell you this is on the test. There's a phenomenon called Brownian motion that keeps those particles suspended in that mixture. What is Brownian motion? We've learned about it before. It's just the random motion of particles of the two things that are in there, whatever your colloid is, and they basically hold up those particles. So it's kind of like if you had a balloon, you were trying to suspend that balloon, and you just kept hitting that balloon to keep it up. That's the idea of Brownian motion. Okay. All right. Define adsorption. That is the attraction of a substance to the surface of a solid. Okay. The attraction of a substance to the surface of a solid, and that is electromagnetic attraction. Okay. That's going to cause something to stick to the surface of a solid. Number 16, not on the test, we'll just go through it really quick. Why is a solution of soap and water more effective than pure water removing oily dirt from your hands? You get a picture of what soap looks like at the end of chapter 12, and you've got a polar end and a non-polar end of this soap molecule. and the nonpolar end sticks into the dirt or grease and leaves that polar end out. And so you have this polar end out. Well, we know that water also, as I drew, is polar. And so that allows the water to literally pick up those soap molecules and carry them away. It's pretty cool. So you get all these soap molecules, the picture of that at the end of chapter 12, stick in the dirt clumps or the grease clumps, and then the water comes along, and those water molecules hook on to the soap molecules, and then they just lift that dirt and that grease away. All right, pretty neat stuff. I mean, that's really incredible. Now chemically we didn't understand that when they first started making soaps, right? But now we understand what's taking place when we use a soap or a detergent. Okay? All right, we're going to come back to problems that matter for your test here in a little bit. I want you to go to chapter 13 now. So open up your chapter 13 review at this point, and we're going to go into chemical kinetics at this point. All right? Chemical kinetics. All right, and I'll leave some of this up here for right now. Let's see, I think I can erase that. I'm going to cough. All right. Okay, question number 1. What two measurable quantities are used to define reaction rate? Those are change in molarity, all right? So change in molarity over change in time. That's the reaction rate. So as a reaction takes place, and you know the reaction charts that you should have studied and looked at, what's actually happening as the reaction takes place is that the amount of the substances that you're combining reduces, the reactants reduce in molarity and over a certain amount of time. Okay, so reaction rate is change in molarity or concentration over time. State the basic premise of the collision theory, and this is a big part. This is chemical kinetics, and so you really need to understand this, and they really try to make it simple for you to get a hang of, but basically collision theory says this: collision between reactant molecules must occur for there to be a reaction. Okay, so as I want two things, and keep in mind, this is not mixing to make a solution. Okay, totally different thing. We're moving on to something else. Now we're moving on to getting these things not to just mix together, but to actually react together so that you have two reactants that come together to form new products. Okay? So in order for that to happen, you have to have a favorable collision. And remember, they can collide in different ways, but if they don't collide favorably, nothing's going to happen. They're going to bounce off each other. If they collide favorably, then we can have a reaction. The greater the frequency and the greater the energy of collision between reactant particles, the greater the rate of reaction. So if we can increase how these molecules hit, if we can get more of them to run together, if we can get them to run together in greater energy, you've got better opportunity for there to be a reaction that takes place. And so you did that in the second lab, which you did, which was really cool, watching these reaction rates when you had room temperature reactants, and then we had cold reactants, and then we had hot reactants, right? And you got to actually see with that phenolphthalein in there how the reaction took place. Very, very neat. And so how can we get reactions to take place faster? How can we increase the reaction rate? Well, greater concentration, you learned in that lab, right? If I pour more of the reactants together, if I put them together, you've got more molecules running around, and then you have a greater opportunity for a favorable collision to take place. All right? And then I can also raise the temperature. Why? Because raising the temperature gives those molecules more kinetic energy, and so they're going to be hitting each other at a higher energy, and those higher energies are necessary to break the bonds, right, in your reactants. So you got to break the bonds in your reactants, get them to recombine with one another to form a new product. Okay, so two things you can do there: increase the concentration, increase the temperature. You've increased the reaction rate. All right, so that's number 3, by the way. How does raising the temperature of a substance affect the number of collisions between molecules? The greater the temperature, the more collisions occur. better to say there, and it's true because there's a lot more movement going on, right? But also they have a higher energy collision as well, and so that really helps, okay? More collisions and higher energy collisions. Number 4, why does the orientation of colliding molecules affect the likelihood of a chemical reaction between them? All right? So again, because molecules are made up of 2 or more atoms, and these atoms have shape. Remember our different shapes that we had back when we studied molecular structures? And I just showed you water. Water has a shape. We have tetrahedral and all those. So they have different shapes. The molecules colliding have different shapes. So the collisions in some orientations encourage a reaction, and there's a picture of this in your book, where it works. If you have 2 that hit each other just right, it's more likely the bonds are going to break. But there are some collisions that cause the molecules to simply bounce off, as I shared with you earlier. Okay, number 5. 3 factors affecting, I'm going to give you 4 factors. They asked for 3, but I'll give you all 4. 3 factors affecting reaction rate and explain their effects on the basis of the kinetic theory of matter or collision theory. So I already explained this to you. Concentration is number 1, okay? The more molecules they have, the more collisions you're going to have. That's concentration. Number 2 is surface area. The more contact is allowed between the reactants in different phases, allowing more collisions and a greater rate. So you're going to get better reaction if you take a powdered substance than you would if you just took a lump of that substance. And the example they gave that to you was starch. If I take a lump of starch and try to burn it, then it's not going to burn very quickly. But if I take that starch and I powder it and I throw it into a fire, it's going to be explosive because you have more surface area of that starch being exposed, and so it can be oxidized. And that is a chemical reaction, right? When we burn something, it's becoming oxidized, and that's a chemical reaction. All right, so surface area. Number 3, temperature. If I raise the temperature, I'll increase the reaction rate. And then number 4 is the concept of a catalyst. And we learned about a catalyst. And what a catalyst does is provides a lower energy pathway for the reaction so that more molecules have the energy to react. All right, so a catalyst provides a lower energy pathway, an easier path than the regular path of reaction. Remember that a catalyst is not consumed in the reaction. You can actually get all that catalyst back after the reaction has been performed, which is pretty cool. All right. Number 6, what is the activation energy of a reaction? What happens when molecules collide with less energy than this? All right. So the activation energy, if we look at that diagram of our reaction, the activation energy is that energy required to get that activated complex to take place. All right, so that's your activation energy. And so this is an energy graph, all right, and you should right off the bat recognize, just while we're doing this, is this exothermic or endothermic, this particular graph? All right, you should be able to jump on that right away. This is exothermic. And we know that because the reactants over here, I know that's small, but so this is the reactants, I'll put a big R there, have this much energy, whatever that level is, okay, and they could measure it, and your products over here have this much energy. All right, so which is higher? Well, your reactants have a higher energy than your products. Your products gave off energy in the form of what? What do you feel when something gives off energy? You feel heat, right? So when this happened, these products that came out ended up giving off energy, so that makes this an exothermic reaction. The energy of the products is less than the energy of the reactants. Okay, the energy of the products is lower than the energy of the reactants. That is exothermic. Your activation energy is the amount of energy required to get this product to react. And actually, it's going to be from here, okay? And just to kind of finish our diagram out, the difference between our energy of our reactants and our energy of the products is this right here, and you should recognize that as delta H, okay? And that is the heat of reaction, the heat of reaction. And some reactions give off heat, those are exothermic. Others require more energy, those are endothermic. So it would look the opposite of this, right? An endothermic reaction would look like, get this over here, it's going to look like that, okay? Going to require a whole lot more energy to get this reaction to take place, and then that energy, so there's going to be, the reactants have less energy than the products, okay, so that's endothermic. So the delta H can be positive or negative. In this case, delta H is negative because it gave away, it lost heat. In this case, delta H is positive because it's retaining heat rather than giving it off, okay? That was a lot of extra information. I thought I'd grab it while we could, while we're talking about this. So, the activation energy is the minimum energy necessary to react, the very least amount. So remember that. It is the minimum amount required to react. Okay? It's not the maximum. We don't know what the maximum is, but we know we have to at least get here. The minimum that we have to have is this much energy to get this reaction to take place and for us to have that activated complex right there. Okay? And so what happens if we don't get there? What happens if we only get to here? That's the next part of the question. Well, the simple answer is nothing's going to happen. Those molecules are just going to run around and bump into each other and bump off each other, and there's no damage done. If you remember the illustration of, you know, the accident, the car accident, right? If you're not going fast enough, you don't have any damage done. Well, okay, if we don't have enough energy, no reaction is going to take place. Number 7. In your own words, explain the role of an activated complex, also known as transition state. So that's up here, y'all, okay? This is your activated complex or transition state, right? And that is when they're coming together, the bonds are breaking. It's a highly energized state that is very unstable, and it's not going to stay that way for very long. But that's what happens when they collide. The bonds are breaking, and they're forming into something new. It's that activated complex. All right. It's a high energy state in which reactants are joined together so they can split to form new compounds. Okay. So they come together for a microsecond, and that's the activated complex, and then they're going to turn into the new thing that it is that we're trying to form, okay? Number 8, if a reversible reaction is exothermic in one direction, okay, so we'll say this is a reversible reaction, it is exothermic in one direction, then can it ever be exothermic in the other direction? And the answer to that is no, okay? If it's exothermic in this direction, then by logic, okay, we go left to right in this direction. By logic, if I was going to try to undo this, it's going to be endothermic in the other direction. All right, so it's going to look like this, right? You can see the low point here, and then the high point here. The products become the reactants, right? And then the reactants become the products. We're trying to get back to our original reactants that we had in the beginning. Okay, so if it's reversible, and not every reaction is, then it will be the opposite of what it was in the beginning. How does a catalyst affect the activation energy of a chemical reaction? What effect does this change have on the reaction rate? So bottom line, it lowers the activation energy. So a catalyst is going to come in here and actually take this curve where it used to, I had to get up to here, but now with a catalyst, it provides a lower energy pathway. And if you remember from the lesson, sometimes you see a little dip and then you get your products, right? Okay? So it requires a lower activation energy, which provides more energy for other molecules to get activated, and so it makes the reaction proceed more efficiently, more quickly, okay? So it lowers, you need to know, catalyst lowers the activation energy. See that? We did have it up here. Now we have less energy. A catalyst did that, okay? So it lowers the activation energy, and then that increases the rate of reaction, okay? Increases the speed, how fast the reaction is taking place. So it's going to shorten the time, right? It's going to happen in a shorter amount of time. You saw that in your lab, okay? All right, let's see. Number 10, how does the catalyst affect the overall net energy change for a reaction? The net energy change is this guy right here. Okay, y'all see that? That's the net energy change between the reactants and the products. Did the catalyst affect this at all? No, because the energy here and the energy here remained the same. The activation energy was lowered, but that did not change these two things, which is what establishes our enthalpy of formation or heat of formation. So the catalyst does not affect your delta H. Does not affect your delta H. Distinguish between homogeneous and heterogeneous catalysts. Which type is found in automotive catalytic converters? Okay. All right, so very simple. Homo means same. Homogeneous catalyst exists in the same phase as the reactants. But a heterogeneous catalyst is not in the same phase as a reactant. Okay, so if you have a solid catalyst and a gaseous reaction, that's heterogeneous. If you have a liquid catalyst in a liquid reaction, that's homogeneous. All right, so you learned from your book, if you read about it and listened to the lecture, that a catalytic converter has these tubes, this kind of mechanism in there that has palladium and platinum metal in it, and that catalyzes, this is why it's called a catalytic converter, the reaction or the change of the exhaust fumes that are coming out of the engine to make it better gaseous emissions, okay? So the gas from the engine the exhaust from the engine is forced through the catalytic converter. That catalyzes the reaction so much quicker. It passes through and you get cleaner air on the other side, right? And interesting in the text, it said that in many cases, the air that you get out of a car is cleaner than the air that was taken in by the car, okay, because of a catalytic converter. All right, point of this question is that a heterogeneous or a homogeneous catalyst? Well, you have a solid palladium and platinum catalyst, and you have a gas going through it, and so that is a heterogeneous. They are not the same phase as each other, heterogeneous catalyst. What term refers to proteins that function as catalysts? So this is in a biological processes, plants, animals, that kind of stuff. Proteins that function as catalysts are called enzymes. One of those enzymes that was talked about in the text is called catalase. And it is a miraculous enzyme that allows our bodies to process hydrogen peroxide that would otherwise kill us. Fearfully and wonderfully made, just like Mr. Ridgely said. Very cool. Define an inhibitor. An inhibitor is a substance that slows the rate of a chemical reaction, often by blocking the action of a catalyst. So that makes sense. It inhibits the chemical reaction. Number 14, why is the slowest elementary reaction in a proposed reaction mechanism described as the rate determining step? The rate, and here's the answer, the rate of a reaction is limited by the rate of the slowest step. Okay, it just makes sense. Now, that goes back to, the elementary steps of how a reaction takes place. Remember, it doesn't all just happen at once. It happens in these theoretical steps. And whichever one of those steps is the slowest is the rate determining reaction. That just makes sense because it's taking the most time, right? And his illustration that he gave to you is really good. If you have a 4-person relay team, which team member is it that sets how well your team is going to do? Well, it's really going to be your slowest one. is really the one that determines the quickness or the speed of your team, okay? All right, so remember that, the slowest step. All right, that is it for the concept information. Now, with the little bit of time we have left, I need to move through these fairly quickly. I'm going to go ahead and continue on and record this. So you can stay on, you can watch it later, but we're going to go through several math problems that you need to know for your test, okay? I will tell you that you will be given formulas such as these that are up on the board. You need to know which formula is necessary for which problem, because I'm not going to tell you that. But let me go ahead and erase this, and we'll go ahead and do some of these problems. So you're going to need to know how to do a molarity problem. How to do a molarity problem. So this one's going to be calculate the molarity of the solution prepared by dissolving 249 grams of potassium iodide in water to make 500 milliliters of a solution. All right? Now, what were we asked to do? Calculate the molarity. Okay, that should tell you right off the bat which formula I'm going to use. That is my capital M, molarity, capital M. What is the formula for molarity? M equals moles solute over liters of solution. Okay, so in order for me to do this problem, I've got to know a couple things. First of all, I got to know what the solute is. The solute is the thing being dissolved, okay, and that's potassium iodide. I need to know how many moles I have of that. That's a fundamental chemistry math problem that by now you need to have mastered, okay? How can I find the moles of solute? Real quick before we do that, the other thing I need to take note of in my problem is that I was given the solution in milliliters, but my formula is asking for liters, so be careful about that, all right? So how do we find out how many moles we have if we've been given 249 grams? That's not moles, that's mass, right? So I've got to figure out grams per mole, all right? So that I go to my periodic table and I figure out for iodine that I have on my periodic table 39.10 grams per mole. How many iodines do I have? Just one, okay? In your problems, if you had, like, for instance, CaCl2, okay, you've got one calcium, you have two chlorines. That's going to matter here, all right? I didn't give you this an example. Maybe another one will get it. Okay, so I have one mole or one molecule of potassium, all right, so I multiply by 1. 39.10 grams per mole. I just went ahead and put it up there just so we could see it. Then I take my iodine, okay, and I have 120, according to the periodic table, 126.9 grams per mole. Again, I only have one of those, so that gives me 6.9 grams per mole. What do I do with those? Ryan? Are they answering? Okay, I add them together. So I'm going to add those together and I get 166.0 grams per mole. All right, so 166 grams of potassium iodide is going to give me 1 mole. I have 249 grams. Quick question, do I have more than 1 mole or less than 1 mole? Well, I have more, don't I? I need 166 grams to make up 1 mole. I've got 249. How many moles do I have? I simply take the number of grams given to me, 249 grams, right, of potassium iodide, divided by the grams per mole. Divide that out, and you will come up with an answer of 1.5 moles. All right, that's the first number that I need for my problem, right? So molarity equals moles of solute, 1.5 moles, over liters of solution. Well, I was given milliliters, so I need to convert that to liters, so I simply move that decimal over, and I get 0.5 liters. Do the math on your calculator, 1.5 divided by 0.5, and you're going to find out that you have a 3 molar Ki solution. What does that tell a scientist? It tells him how concentrated this is, okay? So it's not highly concentrated, it's a 3 molar concentration solution, all right? Okay, so leave that there for a second, or you can pause. I don't have to leave it up there. Pause if you need to get that down. All right, I'm going to erase because we got to move on to the next one. Whoa. Whoa. All right, the next one is going to be calculate the molality. All right, and that's little m. All right. Calculate the molality of a solution of 6.9 grams of glucose. And we have a chemical formula of glucose, so this will be good for us. We can practice this. C6H12O6 dissolved in 125 grams of H2O. Okay, what's the formula for molality? Molality equals moles of the solute over kilograms of solution. Of solvent. Almost got that wrong, of solvent. All right, once again, I've got to find moles. How many moles do I have of sugar or glucose? And then this is given to me in grams, so I need it in kilograms. And same thing, I'm going to move that decimal place over 3 places, right? 1, 2, 3. So it's going to be 0.125 kilograms when we get to that step, all right? And so we're going to go through this together. So the first place you're going to go is where? To get your moles. Well, you're going to go to the periodic table, right? You got to go to the periodic table in order to know how many moles you've got. So we're going to do glucose. Glucose is made up of carbon. Okay, so let's do that. Carbon. And what is carbon's grams per mole? You have 12.01 grams per mole. How many carbons do I have? Times 6. We'll go ahead and do the math on that. That's going to be equal to 72.06 grams per mole. All right, then we have hydrogen. That's one you should remember. We do it all the time, 1.008 grams per mole. How many do we have? 12 of them, right? And that gives us 12.096 grams per mole, right? And then we have oxygen, another one that's very common to us, 16.0 grams per mole. And we multiply that by how many? 6 is correct. Good answer, good answer. Well, that gives us 96.00 grams per mole. What do we do with those? That is right. You said it. You add them. Okay? Go ahead and punch all those into your calculator, and we're going to get a molar mass. That's what we call that, a molar mass of, and we're going to do significant figures on this, 180.16 grams per mole. 180.16 grams per mole. Is that what I needed? No, I need moles. How do I do that? I take what I'm given, 6.9 grams of glucose over my molar mass, 180.16 grams per mole. I do that problem, that's going to cancel my grams, and moles is going to come to the top, and I'm going to end up with 0.038 moles of C6H12O6. All right, there we go. I got my moles. Now what can I do? I can plug that into my formula over here to find molality. Molality is moles of solute, 0.038 moles over kilograms of solvent. I changed that already, 0.125 kilograms of water. Okay, and that's going to give me 0.31 molal, little m, okay, that's not mass, that's molal, a 0.31 molal solution. Okay, we would just write that, C6H12O6. 0.31 molal solution of glucose. Okay? Now, what can we do with that? What can we do with that? Well, one of the things that we can do with that is figure out the boiling point elevation and the freezing point depression. We haven't talked about that yet, okay? The boiling point elevation, the freezing point depression. Those are, what kind of properties are those, y'all? Starts with a C. Those are colligative properties. Colligative properties. So they're not affected by the type or the what's the word I'm looking for? The properties of your solute, but by the number. How concentrated is it? Okay, so the more of those molecules you have. Doesn't matter really whether it's NaCl or CaCl2. What matters is how many of the particles are in there. Those are colligative properties, okay? And so the more of those things you collect, the more it's going to change these two things in particular. Also, vapor pressure is another colligative property. But your delta T, your change in boiling point, or your change in freezing point, okay? So we're going to do two of those problems, and we're going to use this information. So here's the question. What is the boiling point? What is the freezing point and the boiling point of this solution? What is the boiling point and freezing point of this solution that we just did right here? So this is kind of a different problem, but using the same information. And the formulas you're going to need to know for that. And by the way, I give you formulas. You just have to know which one to use and when. So delta T B is equal to, okay, your delta TB is equal to molal concentration times that constant, that boiling point constant, okay, which you find on a chart which will be given to you on the test, but it's on the chart on page 211. All right, and then the freezing point change is equal to MKF, right? All right, super duper easy. This is really easy, just multiplication, but let's make sure we understand the concept. We call this the boiling point elevation. In other words, the boiling point for water is how much? What's the boiling point for water in Celsius? Normally, for distilled water, is 100 degrees Celsius, right? Okay, and then the freezing point for water, for distilled water, is 0 degrees Celsius, right? Okay. The reason we have to say distilled water is because we can't have any particles in it. If you've got some calcium in there, if you've got some magnesium in there, you've got some other stuff in there, and that's our water that comes out of the tap, has things in solution that change that. So if you boiled water at your house that just came out of the tap, you should see that it should raise the boiling point a little bit. Your boiling point should be a little higher, right? Same thing is true with your freezing point. Your freezing point, when you have something in solution in the water, depresses. In other words, it has to get colder. It's going to require colder than 0 degrees in order for that water to freeze. So how do we figure that out? Well, we're going to take this number that we just found. That is your m, little m. You're going to take that number and plug it into these formulas using the constant that they give you. All right, so I'll take it down here. Delta TB equals 0.31 molal. I'm going to leave off the glucose, times the constant for water for the boiling point. Make sure you watch these, okay? So KB is 0.512. And there are units after that. I'm just going to leave those off right now. We're going to end up in degrees Celsius there. All right, so I multiply those two together, and I'm going to get 0.16 degrees Celsius. All right, so if you did the math on that, that's what you should get. This is my boiling point elevation. So what do I do to find the boiling point, the temperature of boiling? I'm going to add this, because I know it's going to require more heat. I'm going to add that to my normal boiling point, and that's going to mean that the new boiling point is 100.16 degrees Celsius. It's going to require a little more heat. Not too much. Really not too much. All right, what about the freezing point depression? 0.31 molal times, and you got to go back to that number. Make sure you get the right number, and it's 1.86 degrees Celsius per molal. 86. And I'll go ahead and put it in there. Degrees Celsius per molal. That way you can see the molals cancel, right? And we're just left with degrees Celsius. And you do that math, and you get 0.58 degrees Celsius. But remember, it's elevating the boiling point, but it's decreasing the freezing point. So this one I'm going to subtract. And that's going to give me negative 0.58 degrees Celsius. That's why when they add salt to the road, or calcium chloride to the road in areas that get ice on the road, it lowers the freezing point, which means it allows some of that ice to melt. Okay? At some point, it's not going to work, right? If it just gets cold enough, you can't get enough calcium chloride or salt in there to lower that freezing point down far enough. But in any case, there you go. All right, so the new boiling point is 100.16 degrees Celsius. The new freezing point is negative 0.58 degrees Celsius. Make sure that you watch the problem and what's asking for it. If it asks you just for the boiling point elevation, in other words, how much did it increase by, that's what they want. If they want the freezing point depression, this is what they want. If they ask you for the new boiling point, freezing point, you have to make sure that you know to add or subtract that. Okay? All right. Very good. Very good, very good. Let's see. The next one we're going to do is, got an example here I want to work with you. All right. This has to do with, in the lab, making new concentrations of a solution for you to use in the lab. So this is a very practical thing. I use it all the time when I'm preparing substances in the lab, especially those that are in aqueous solution. Like we need a 0.5 molar concentration of hydrochloric acid. Well, the hydrochloric acid I buy is in a high concentration. It's probably a 12 molar concentration, and I want to get it down to a half molar concentration. Then I need to know how to do that, okay? And this will be the last problem we do, so we'll be wrapping up here real quick. Sorry, Pastor Brandon, for holding you so long. All right, so the formula you need to know for this. So if they're asking the question, how would you prepare a 12 liters of 3.0 molar ammonia. Does anyone remember the formula for ammonia? There it is, okay? How would I prepare 12 liters of 3.0 molar concentration of ammonia from 15 molar? 15 molar concentration of ammonia. How would I do that? Okay, so in other words, let's just say I bought a bottle of high concentration ammonia, and it's too much, right? Because I don't want reactions to go nuts in there. If I use that high molar concentration, we could have something very explosive happening, right? It's very volatile, would be very bad. So I want to dilute it down to 3 molar. Does that make sense? How am I going to do that? And I want 12 liters of it. I guess I want a lot of it to clean with, okay? Clean with ammonia, we want 12 liters that I can clean with, and how am I going to dilute that down? Okay, so the formula you need to know, you should know this, V1 M1 equals V2 M2. All right, so here's what you need to know, and it's out of order from what the question is. What I want to end up with is 12 liters of 3 molar ammonia. That's what I want to end up with. So this is my V2, this is my M2. That's what I want to end up with in my second round, my second step, right? And then my original M is 15 molar, all right? And I need to know how much of that I'm going to need to add to this 12 liters of water. So how much of that 15 molar NH3 do I have to add together, combine together, to get 12 liters of 3 molar? All right, simple math. So then you're going to have V1 times 15 equals 36 liters per mole. All right, per molar, not mole, per molar solution. I divide both sides by 15 to get them to cancel. That's going to cancel those. And so then my volume is equal to 36 divided by 15, right? And you get 2.4 liters. So what am I just saying there? I need 2.4 liters. I'm going to mix 2.4 liters of this highly concentrated ammonia that I have in order to get 12 liters of my solution, okay? So I've got a big container, right? And I'm going to carefully add the 2.4 liters of that ammonia into my water, right? And once it's diluted enough, I would just add that in there and get it all mixed up nice, and then carefully add water, add water, add water until I ended up with, I've got a marker on my container, till I came up to 12 liters, and then I've got 12 liters of a 3.0 molar of ammonia solution, okay? So V1M1 equals V2M2, and then you would just say how you would combine those. Again, carefully combining. Diluting it, right? Okay, last thing that you need to know for your test is understanding the relationship between temperature and reaction rate. Very simple, very quick. For every how many degrees does the reaction rate double? For every how many degrees does the reaction rate double? He said it several times and it was in your text. You should know it. So the answer is for every 10 degrees Celsius, my reaction rate doubles. Okay? All right. So if I told you that my reaction at 25 degrees Celsius, which is basically room temperature, my reaction rate is I'm reacting at 0.005 moles per second. Okay, I'm reacting at 0.005 moles per second. If I increase the temperature to 35 degrees Celsius, that's a 10-degree difference, right? This reaction rate is going to do what? It's going to double. All right? And that's going to give me 0.010 moles per second. Well, what if I did that again? 45 degrees Celsius. Multiply it by 2. That's going to give me 0.020 moles per second. Okay? I can keep going and keep going and keep going. One more time. We'll just do it one more time. 55 degrees, and then we'll let y'all go. Again, it's 10 degrees up, 10 degrees up, 10 degrees up. Multiply it by 2, 0.040 moles per second. The hotter I get it, the more moles per second are going to react in general. For every 10 degrees Celsius, it's going to double. Okay, so you need to be able to figure that out and understand that process. Okay. All right, I think that is about all. If you have taken good notes, if you got good answers on your reviews, if you go back through any quizzes that you have or any assignments that you've done, you should do fine on this test. I'm just making sure I've given you everything. I believe that I have. You'll have many different types of questions, fill in the blank, multiple choice. You will have some of those modified true and false. Make sure you read the directions for each of the problems. So you get, like for instance, on your math, make sure you're doing significant figures and putting units down. I think that's about it. Thank you for your time today. Thank you for Pastor Brandon for your time today. And God bless you and have a great weekend.